Hi, so in this video, I'm going to be going over a couple of things. The first thing being where all of my files can be found, all the schematics, all the simulations that I've been running, where they can be found on the drive. And in the second part of this video, I'm going to be discussing the simplest model for the UCC 25640X controller, how you can change parameters around, and how you can run simulations on them. So those are the two things that are going to be discussed in this video. So here you can find all of my files mostly in the 12 volt to point of load as well as the 48 volt to 12 volt folder. If we come here to the 12 volt to point of load folder, you can see a report that I made in February about the 3 different solutions that I found. One from Analog Devices, and here you'll also find comparisons, various characteristics about them, as well as simulations that I ran on them. So that's where this is found. And each one of them are separated into different files. So here I have the Analog Devices model, a schematics over here that I use to run each simulation. Here I have pictures of each of their simulations, and I also have the data sheet uploaded right here. Over here I have one of the Texas Instruments model and the schematic that I was using, as well as the input and load transient tests and its data sheet over here. And over here, I also have the final solution that I was looking at, as well as its input and load transient tests, its schematic that I was working with, and its datasheet. Now, if you come back here, if you go to 48 to 12, all of my stuff is over here in Jason Guico LLC. And just as a reminder, I was responsible for just designing the LLC on Simplest, as well as working with the HHC controller, and working with it from there, running simulations, AC response, frequency response, transient response, all that. And yeah, so they're over here. Actually, over here you can find a couple of my notes. So over here we just have notes of the LLC converter. Over here I have design considerations, so various equations that you could use to design your own LLC converter. So here I have a TINA schematic of an LLC converter that I personally designed. This one just goes from 48 to 12, but it doesn't necessarily meet any of our other design specifications. It doesn't go high enough with regards to output power. It also uses PWM signals at the switching bridge instead of using a gate driver. So it's a very bare bones schematic of a TINA, or bare bones schematic of an LLC converter that I was just using to play around with, and it was based on the parameters set by Stan's design on Simulink. So yeah, that's where you can find it. So also in my folder, you'll find a folder of the UCC 25640X simplest model of the HHC controller that I was working with, as well as the simplest model that was provided straight from Texas Instruments. So if we open it here, you'll see that I'll have 2 schematics over here, a test bench for the 48 to 12 volt converter, along with the controller with ideal components, and here I have one with real components. So this one's using real MOSFETs at the switching bridge and real diodes at the rectifier. Here I have a transient simulation of the real components model, and here I have one of the ideal components. Here I have a transient at the switching bridge for the real components, and here I have one for the ideal. So in order to even run the schematic or open the schematic in the first place, what you're going to want to do is go back to this folder and download this entire UCC 25640X simplest model folder. I apologize in advance because this folder is actually quite big, mostly because of the real component simulations, which were about 5 to 10 gigabytes big. So it'll take a while, but after you have it all downloaded, you'll be able to open these 2 files, and you'll be able to run simulations on them and change some parts around, change parameters, whatever you want to them. And I'll be going over how to do that next. So after you download the folder in My Files, you're going to have access to all of the schematics that I was working with, as well as the graphs that I produced. So all the transient graphs, as well as the ideal and real component schematics. So let's take the ideal component model as an example. So if you click into it, assuming that you already downloaded Simplest, it's going to take you directly to the schematic. So in the schematic here, we have the LLC Converter, and we have the setup and measure tools over here, as well as the optocoupler over here, which is actually the reason why you have to download the entire folder, because without downloading it, you won't have any access to both the optocoupler as well as the setup and measure blocks over here. And it'll render this entire file useless. So here we have, ideal switches over here. We just have generic switches given by Simplest. We have the resonant tank over here, the transformer, and we have the rectifier over here, as well as the output over here on this side. So the resonant tank's parameters, as well as other components over here, their parameters can be changed by pressing F11. So pressing F11 brings up this little window over here that has parameters and their settings. So for example, if you want to change the input DC voltage, you can change that over here. We currently have it set to 48 because that was the focus of this entire this specific LLC. And we also have output current over here. So we currently have it set to 30. And the reasoning behind this is that, the reasoning behind being able to set your output current is that we're not necessarily relying on a resistor to set our output current. Instead, we are setting the output current directly. And over here, we also have the current after the pulse. So after it pulses during your transient response, it's going to pulse to 35 or whatever you set it to. You can also change the pulse duration, or also when the pulse happens over here. And yeah, over here is pretty important. We have the resonant tank parameters that you can change. Currently, these are set to values such that our resonant frequency is around 100 kilohertz, but any of these parameters can be changed. LR1, LR2, magnetizing inductance, and the resonant capacitor can all be found over here. And down over here, we have more parameters that I personally haven't really touched, but Stan has. Here we have the VCR capacitor divider, which can be found over here. Personally, I didn't really look into it that much, but if you look in the UCC 25640X datasheet, you'll be able to find more information about it. So after you've set all of the parameters to your liking, to whatever you wanted to simulate it at, in order to simulate, you're going to want to come to Simulator and choose your type of analysis. So for example, if you wanted to run a transient, it would normally be like this, and you'd choose transient. And now it has a checkbox marking transient. So now you could set your stop time. You can start when to start saving data. You could also change the number of plot points. And then all you have to do after setting that is to run. So after it runs, we have this little window over here that pops up with graphs. So here we have the output current, and we also have the output voltage over here. So if you find an error with the transient response and you don't necessarily see the point in continuing this this simulation, you can simply go back to this window over here and press abort. Similarly, you could also press simulator over here and press abort also over here. So you have other options. And now that we have this graph, you can also go to file and you can save the graph as anything you want. You can save it as a PDF, save it as a picture, and then it'll show up in the same files where all the schematics and graphs are currently found right now. Similarly, you'll also, after you X this out, you're also going to find other sort of measurements that it's been making. For example, current through the current, VDS, you can find VCR, a lot of the other parameters over here, or other measurements over here. And over here we'll find the gate driver, or the what would be the gate in a real MOSFET, but over here would be this specific voltage that's measuring, as well as the switching voltage. And yeah. So as a note, if you want to run an AC or AC analysis on this, you're going to want to press pop and AC, because without pressing pop first, it wouldn't allow you to run the AC analysis in the first place. So after doing so, just press pop, AC, and then run. And then you're going to wait for the pop analysis to run. And then you're going to wait for... So after that finishes, it's going to go straight into the AC analysis. I'm just going to abort this. And yeah, so if you have a graph that you've downloaded, for example, or a PDF of the graph, you're going to come to this specific file, and then you're going to choose the specific graph that you want to view. I'm going to use the transient response for the ideal components that I chose. So assuming I had allowed the component to, or the simulation to run completely, this is what the output voltage and current was going to look like. So this is the transient response. So over here, obviously, we could see that we're going from 30. It goes and pulses up to 35 around 20, and then pulses back down after about 10 milliseconds. So it's exactly fitting what I chose to be the parameters over here. So 10 milliseconds for the pulse duration, and then when the pulse actually happens. So yeah, so as we can see here, the there's a bit of an overshoot, and then it reaches 12 very well. And despite the change in current over here, it remains at 12. And eventually, after it returns back to 30, it goes back to 12. So it has a very good transient response. And as a note, if you set the voltage or the input current, let me just change this real quick. So if we go back to transient, if we go over here and let's say you choose a current that's too high, you're going to notice that the output voltage never actually reaches 12 volts. In fact, it fails pretty spectacularly at a voltage much lower than it should be. Like if we set it to 100 or 130 even, and 135. What your graph is going to look like, I'm not going to run it right now, but what it's going to look like is this. So this is an example of what would happen if the transient simulation was to go wrong, where the output current was set too high and the LLC converter was unable to produce the graph that it wanted to. So we're assuming that this is mostly because that this specific model from Texas Instruments doesn't simulate some important features of the UCC 25640X, including the ZCS fault detection and correction. So we're assuming it's some sort of issue with that, but otherwise we're not quite sure about why it doesn't reach steady state, nor does it reach 12 volts at all. And there's also this weird ripple in the current that's going on that we don't quite understand. So that's something to just note if you're running a simulation on this model. So that was my video. I hope it helps, and just be sure to check out Stan's video and Tristan's video for both phase shift modulation and hybrid hysteretic and direct frequency control simulations and information. Thank you.